Okay, picking up where we left off, you might notice a little difference in the background here. Coming to you from my office, there was a mistake in the video. So this is a kind of a retake of replacing a video that someone had already watched and found a mistake. So not that you care about any of that, but I thought I'd throw it in there if you notice that things look a little different. That I'm coming to you from my office. So we've looked at limits at infinity. We've looked at them graphically, and we've looked at them by making charts. Graphically and charts are good ways to understand what's going on, but they're not good ways of finding perfect answers. Finding perfect answers, we need an analytical format. So that's what we're doing here, finding something analytically. So we got a little fact here. It's going to allow us to do it analytically. And it says if R is a positive rational number and C is any real number, then the limit as x goes to infinity of C over x to the R equals 0. Furthermore, if x to the R is defined when x is less than 0, then the limit as x goes to negative infinity of C over x to the R equals 0. Okay, so there it is in mathematical pureness. What this is saying is this. This means limits of the form. And if I allow myself to think about substitution for a minute. Now, I shouldn't substitute infinity or negative infinity. They aren't numbers. You should only substitute numbers. But now that I said that we shouldn't do it, let's do it anyway. Limits of the form constant over plus or minus infinity go to 0. That if I think about, and let's zoom in just a little bit here, so you can see it a little bit better. If I think about plugging in infinity here, and so that I have infinity raised to the R, or negative infinity raised to the R, that when you're at infinity and you exponentiate it in any way, you stay at infinity. So if I think about substituting, which I shouldn't do because infinity is not a number, we'll learn later that infinity minus infinity isn't necessarily in 0. And infinity divided by infinity, not necessarily 1. So we really shouldn't do substitution. But in the case of exponentiation, infinity raised to an exponent, or negative infinity raised to an exponent, as long as it's defined. And that's what this part is saying here, that if x is negative, so if I'm going to negative infinity, as long as we're defined, as long as we avoided an imaginary number, constant over infinity goes to 0. Any limit of that form goes to 0. So now that I have this little basic fact, I can do a few problems. As long as I remember that when we're dealing with limits at infinity, as x approaches infinity or negative infinity, constant over infinity goes to 0. So given that fact, we can do a few problems here. Now here's the logic here, that everything you learned about limits before, the rules for limits before, still true when we approach infinity and negative infinity. So in this case, what I'm saying here is that I could break this down into 4 separate limits. And I'll write that cube root as x to the 1/3. Then everything we learned about limits before still true, meaning the limit of a constant still a constant. So the 3 and the 4 stay the 4, 3 and 4. But now our new fact. This is a constant over infinity. And so it is going to go to 0. And the same thing here, that is going to be a constant over infinity. And so it will go to 0. And so that answer is just 3/4. That you basically have a new limit form. And that when you have a constant over infinity, Because if I allow myself to think substitution for a moment, now I shouldn't, but now I'm still going to do it. If I think substitution, that's going to be infinity to the fifth, which is still infinity. And that's going to be the cube root infinity or infinity to the third, still infinity. And a constant over infinity always goes to 0, so 3/4. That's the only form you know right now, is a constant over infinity. So when I look at this one, this isn't in a known form. I got as x goes to infinity, but this is not in the form constant over infinity. And so I have to rewrite it. And the trick here to rewrite, divide all terms by x to the highest exponent. Meaning this, and I really should have given myself more room here. So that's going to be 2 plus x to the 1/3 over 3 minus 4x to the 1/2. So now do what I said I was going to do, which is divide everybody by x to the highest exponent. So that's 2 over x to the 1/2 plus x to the 1/3 over x to the 1/2. Really didn't give myself enough room here. 3 over x to the 1/2 plus 4 over x to the 1/2 over x to the 1/2. Excuse the horrible, horrible handwriting. Simplify here. And so here, remember exponents to a fraction. I'm going to rewrite this so it's a little neater. That's pretty pathetic there. So we'll rewrite it so it's a little neater. That's x to the 1/3 over x to the 1/2. In a fraction, I subtract my exponents. So that's going to be 1 over x to the 1/6. 1/2 minus 1/3 is 1/6. And then that's going to give me 3 over x to the 1/2 plus 4. Let's rewrite this so it's actually maybe legible. Love the whiteout. But now that I've pulled that trick, I can do all of these. All of these guys, this one, this one, this one, they're all a constant over infinity, which goes to 0. So I have 0 minus 0 over 0. All those are that new form, constant over 0. And then I still have that 4, or excuse me, new form, constant over infinity. And they all constant over infinity goes to 0. So I have all those zeros in a 4, or 0 over 4, or 0. So there's that one. And so both of those problems hinged on the new form constant over infinity. And we are going to learn some shortcuts in a little bit, but we aren't quite there yet. So getting ready for this problem. Before we get ready for this one, we're going to have to learn a little bit about absolute value. And so we'll do a little bit of absolute value here. So right there you see the official definition of absolute value. The absolute value of x squared, or the square root. Yeah, starting over, algebra view. So first, square root of x squared. So you learned way back when someone told you, probably in algebra, the square root of x squared was x, which is not quite true. The square root of x squared is the absolute value of x. The mathematicians want the square root to be a function, and so they've decided that the square root should always result in a positive answer. And so when the answer is x, or we think the answer is x, since x is a variable and I don't know if x is positive or negative, to make sure it's positive, I slap absolute value around it. Because we want the square root function to be a function, so there only should be one answer. And so very technically, the square root of x squared is the absolute value of x. Just like the square root of 9 is 3. We don't say the square root of 9 is negative 3, we say it's 3. Now talking about absolute value. Absolute value actually has a definition. You were told back in high school or wherever you learned about absolute value, oh, it just makes everything positive. But it actually has a definition, and it's right here, that the absolute value of x is either negative x if x is less than 0, or it's equal to x if x is greater than or equal to 0. So what this is saying is if you're taking the absolute value of something, if whatever you're taking the absolute value of, if it is negative, the way you're going to do the answer is the opposite of whatever you had. So, well, that doesn't make any sense. Well, think about it. The absolute value of -3. -3 is less than 0. So by my definition, the answer will give me, my definition gives me a negative, and then it says take the opposite of whatever's on the inside. That's what this is saying. Take the opposite of whatever's on the inside. So in this case, and those are parentheses, not absolute values, the opposite of whatever's on the inside, so 3. So there's the official definition of absolute value, that if your inside is already negative, the way you're going to get the absolute value is to take the opposite of whatever that inside value was. If your inside's already positive, just keep it. And we will need that definition when we do this next problem, which will be in the last video. So stay tuned for the next video. And that is the end of this.